Hello! Today we're going to dive into the fascinating world of fluid mechanics. By the end of this lesson, you'll be able to define key fluid properties, understand how pressure works in fluids, and apply fundamental principles like Pascal's, Archimedes, and Bernoulli's equations to solve real-world problems. Our main goals are to define density and pressure, explain Pascal's principle, calculate buoyant force, and use Bernoulli's equation to analyze fluid flow. Let's get started. First, let's define what a fluid is. A fluid is any substance that can flow and take the shape of its container. This includes liquids, like water, and gases, like air. The key difference from a solid is that a fluid cannot resist a shearing force. It will deform continuously. So fluids are substances that flow and conform to their container shape. Now let's talk about two fundamental properties of fluids, density and pressure. Density, represented by the Greek letter rho, is simply the mass of a substance per unit volume. It tells us how much stuff is packed into a given space. The formula is density equals mass divided by volume. For example, water has a density of about 1,000 kilograms per cubic meter. This means that 1 cubic meter of water has a mass of 1,000 kilograms, or 1 metric ton. Air, on the other hand, is much less dense, about 1.2 kilograms per cubic meter. Next up is pressure. Pressure is defined as the force applied perpendicular to a surface, divided by the area over which that force is distributed. The formula is pressure equals force divided by area. Think about it this way. If you push on a wall with your hand, you're applying a certain force. If you then push on the same wall with a single finger, you're applying roughly the same force, but over a much smaller area. This results in a much higher pressure, which is why it feels sharper. The standard unit for pressure is the Pascal, which is 1 Newton of force per square meter of area. So to recap, density is mass per volume, and pressure is force per area. Now let's see how pressure behaves in a fluid at rest. This is called hydrostatics. A key concept here is that pressure in a fluid increases with depth. Imagine a column of water. The water at the bottom of the column has to support the weight of all the water above it. The deeper you go, the more water is above you, and therefore, the greater the pressure. We can derive a formula for this. The pressure at a certain depth is the atmospheric pressure at the surface plus the pressure due to the fluid column itself. The pressure due to the fluid column is its weight divided by its area. The weight is mass times gravity, and mass is density times volume. Since volume is area times height, the pressure due to the fluid is density times gravity times height. This gives us the hydrostatic pressure equation, P equals P naught plus RHOGH. Let's work through an example. Suppose we want to find the pressure at the bottom of a 10-meter deep swimming pool. We'll assume the surface is open to the atmosphere, so P naught is atmospheric pressure, about 101,325 pascals. The density of water, rho, is 1,000 kilograms per cubic meter. Gravity, g, is 9.8 meters per second squared, and the depth, h, is 10 meters. Plugging these values into our equation, we get P equals 101,325 plus 1,000 times 9.8 times 10. This simplifies to 101,325 plus 98,000, which equals 199,325 pascals. So the pressure at the bottom of the pool is nearly double the atmospheric pressure at the surface. Next, let's explore a very important principle for fluids at rest, Pascal's principle. This principle is the foundation for many hydraulic systems, from car brakes to construction equipment. Pascal's principle states that a pressure change at any point in a confined incompressible fluid is transmitted undiminished to all points in the fluid and to the walls of its container. In simpler terms, if you squeeze a sealed bottle of water, the pressure you apply is felt equally everywhere inside that bottle. Let's see how this works in a hydraulic system. Imagine two pistons of different sizes connected by a fluid-filled tube. We have a small piston with area A1 and a large piston with area A2. If we apply a small force F1 to the small piston, it creates a pressure P1, which is F1 divided by A1. According to Pascal's principle, this pressure P1 is transmitted throughout the fluid, so the pressure P2 on the large piston is equal to P1. Since P1 equals P2, we can write F1 over A1 equals F2 over A2. Rearranging this, we find that the force on the large piston, F2, is equal to the force on the small piston, F1, multiplied by the ratio of the areas, A2 over A1. This is the magic of hydraulics. If the large piston's area is, say, 100 times larger than the small piston's area, then the force on the large piston will be 100 times greater than the force you apply to the small piston. You can lift a car with just your hand. So Pascal's principle allows us to multiply force by using pistons of different sizes. It's a powerful concept that underpins many modern technologies. Now let's talk about why things float or sink. This brings us to the concept of buoyant force, which is explained by Archimedes' principle. Archimedes' principle states that any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. In other words, when you put something in water, it pushes some water out of the way, and the water pushes back with a force equal to the weight of the water it displaced. Let's break this down. The buoyant force, which we'll call F_B, is the upward force that opposes gravity. The formula for buoyant force is F_B equals rho the VF times VF times G. Here, rho the VF is the density of the fluid, VF is the volume of the fluid displaced, and G is the acceleration due to gravity. The volume of the fluid displaced, VF, is equal to the volume of the object that is submerged. If the object is fully submerged, VF is the object's total volume. If it's floating, VF is just the volume of the part that's underwater. An object floats if the buoyant force is greater than or equal to its weight. It sinks if its weight is greater than the maximum possible buoyant force. Let's try an example. Imagine a solid block of wood with a volume of 0.02 cubic meters. We want to find the buoyant force on it when it's fully submerged in water. Since the block is fully submerged, the volume of fluid displaced, V-F, is equal to the block's volume, 0.02 cubic meters. Now we can calculate the buoyant force. F_B equals 1,000 times 0.02 times 9.8. This gives us a buoyant force of 196 newtons. So the water is pushing up on the block with a force of 196 newtons. If the block's weight is less than 196 newtons, it will float. If its weight is more, it will sink. So far, we've talked about fluids at rest. Now let's shift our focus to fluids in motion, which is called fluid dynamics. The first principle we'll discuss is the continuity equation. The continuity equation is a statement of the conservation of mass. It says that for an incompressible fluid flowing through a pipe, the mass flow rate must be constant. In other words, the amount of fluid passing any point in the pipe per second is the same. This leads to a very intuitive result. If the pipe narrows, the fluid must speed up to maintain the same flow rate. Think about putting your thumb over the end of a garden hose. The water comes out faster because you've reduced the area. The equation is A1 times V1 equals A2 times V2. Here, A1 and V1 are the area and speed at one point in the pipe, and A2 and V2 are the area and speed at another point. Let's work through the example you mentioned. Water flows through a pipe that narrows from a 0.3 meter diameter to a 0.1 meter diameter. The speed in the wider section is 2 meters per second. We want to find the speed in the narrower section. First, we need to find the areas. The area of a circle is pi times the radius squared. The radius is half the diameter. So, for the wider section, A1 is pi times 0.15 squared, which is about 0.0707 square meters. For the narrower section, A2 is pi times 0.05 squared, which is about 0.0785 square meters. Now we can plug these values into the continuity equation. We have 0.0707 times 2 equals 0.00785 times V2. Solving for version 2, we get V2 equals 0.1414 divided by 0.00785, which is approximately 18 meters per second. So as the pipe narrows, the water's speed increases from 2 meters per second to 18 meters per second. This is a direct consequence of the conservation of mass. Our final topic is Bernoulli's equation. This is one of the most important equations in fluid dynamics, as it relates pressure, speed, and height in a moving fluid. Bernoulli's equation is a statement of the conservation of energy for a fluid. It says that the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume is constant along a streamline. Let's look at the terms. P is the static pressure. 1/2 rho v squared is the dynamic pressure, which is related to the fluid's motion. And rho gh is the hydrostatic pressure, related to the fluid's height. A very important consequence of Bernoulli's equation is that if a fluid is flowing horizontally, so the height h is constant, then an increase in speed must be accompanied by a decrease in pressure. This is often called the Bernoulli effect. This effect explains many phenomena, like how an airplane wing generates lift. The curved top surface forces the air to travel a longer distance in the same amount of time, so it speeds up. According to Bernoulli's principle, this faster air has lower pressure, creating an upward force on the wing. Let's apply this to our previous pipe example. We know the water speeds up from 2 meters per second to 18 meters per second. Since the pipe is horizontal, the height h is constant. Therefore, the pressure in the narrower section must be lower than the pressure in the wider section. The increase in kinetic energy comes at the expense of pressure energy. So Bernoulli's equation connects the speed, pressure, and height of a fluid, showing how energy is conserved as it flows. It's a powerful tool for analyzing fluid systems. Let's quickly recap what we've learned today. We started by defining fluids and their fundamental properties: density, which is mass per volume, and pressure, which is force per area. We then explored hydrostatics, learning that pressure in a fluid increases with depth, according to the formula P equals P naught plus Ras GH. We saw how Pascal's principle allows for force multiplication in hydraulic systems. Moving to fluid dynamics, we learned about Archimedes' principle, which explains buoyancy and why objects float or sink. We then covered the continuity equation, A, 1v1, equals A, 2v2, which shows that fluid speeds up in narrower pipes. Finally, we introduced Bernoulli's equation, P plus 1/2 rho squared plus rho gh equals a constant, which is a statement of energy conservation for fluids and explains the inverse relationship between speed and pressure. You are now able to define key fluid properties, understand how pressure works, and apply these fundamental principles to solve problems. I hope this has given you a clear and conversational introduction to fluid mechanics. Thanks for watching.